Okay, hopefully everyone can hear. Welcome, good evening if you're in Europe, or good morning if you're elsewhere. We're here now for Paco and FM's Masterclass in Graph Data Science. I hope many of you joined the excellent session yesterday, which Paco hosted. I won't give a huge introduction to Paco, not least because I don't know how I could describe Paco, apart from as a guru in our space. He's one of the most exciting people that I talk to in the community, a genuine sponge of knowledge, and I always come away from our conversations feeling positively infused and learning a lot. So I'm really looking forward to this session. So yeah, last thing is to just, as always, thank our sponsors for helping make this happen, Semi Technologies and Weaviate. And with that, over to you, Paco.
Thank you very kindly, James. I appreciate it. Alrighty, well, I'm really looking forward to today. I've really enjoyed the sessions yesterday and the community discussion, and also just a lot of discussions that we had subsequently offline on LinkedIn and email and others. So I'm thoroughly looking forward to our discussions here today. And I want to figure out, certainly on this platform, what's the best way to work on this. But I will be sharing my screen. Most of what we'll be going through is available in notebooks, so it works really well to show through the browser. And also you can be having this in a different browser window and going along with it. But I also want to try to shift back and forth so that I can catch questions in chat. And I think just real briefly, while I'm doing this before I start sharing the screen, let me show my face here. I want to be able to monitor the chat also because there may be questions that come up as far as when we're doing the installation. So welcome all. Thank you. This is about graph-based data science. This is a masterclass, and we'll be showing, working in Python, how you can use a lot of different types of Python libraries. There's one in particular called kglab. We've been doing a lot of work to integrate other libraries so that they have common ground. And we'll be working through different use cases using graph-based techniques and showing how these integrate with the popular data science tooling like pandas and matplotlib and numpy and parquet and things like that. So I think probably the best way, we'll see how this works out, but probably the best way for this format is we'll go through some different points. I'll show you from my screen what I'm doing, and we'll spend some minutes doing that, going through whatever code that we're covering, and then I'll cut back to chat because I want to allow for a lot of interaction. I'm not sure that participants will be able to ask via audio, so if I'm sharing something full screen, I wouldn't be able to see without doing some cut back into chat. Also, we definitely want to include breaks during this, and I'll be around during the breaks generally to answer any questions. We've got a few hours here today, and definitely we've got enough material to pack into that time. We will be building off of a lot of the materials that we had yesterday in the talk, and I just want to make those slides available as kind of a general background. So that's one of the first things that I'll put in the chat here. There's this talk. Let's see. Okay, great. And let me change my screen around a little bit. There we go. Good. Now I can see more chat. So I just pasted in. There's the talk slides that we had from yesterday. There's actually a superset of those slides. There's a lot of links and a lot of background information. If there's any particular parts that you want to check for primary sources or other repos, things like that. So that's one set of materials. The other thing, though, is the actual GitHub repo for the kglab project. And I'll paste that in here now. So that's github.com/darwinai kglab. And we're not going to have a large requirement on programming. You know, the idea is if you can work with brief Python programs, 20 lines or so, read and write those, you're probably good to go here. If you want to get set up with hands-on coding side, what you'll need to do is download that GitHub repo, clone it, and so there's instructions, and I can walk through some of this. Let me go back to sharing. If I can get my screen, yeah, there we go. Share screen, Chrome tab. Good. I can just share one tab at a time, it looks like, so that's probably a better thing. If you go to this github.com/darwinai/kglab, on GitHub is our main repository site. And if you're not familiar with using GitHub, they make it very convenient. There's a green button up in the top right here. It says code. And there's a few different ways to work on things. The easiest way I find is if you have, if you copy and paste this URL, it'll say github.com, kglab.get. Okay, so that'll give you a URL, and then go into the command line, and actually I can walk you through it. I'm not going to do the entire thing. Let me share my command line. It's probably better the whole screen. Yeah. So if you're at a command line and you want to install, if you haven't used Get before, let's dig this up real quick. Okay. So if you say for any repo, if you get that URL for the repo, you can say get clone and then give it the URL, hit return, it'll start to download from Get, and it'll create a new directory, which is the name of the repo. In this case, it would create the kglab repo with all the source underneath it. So if you're not set up already, take that step. And once you do that, then you'll connect into a repo. I already have it installed, so I'm not going to overwrite it. But you'll end up with something that looks very much like this, kglab, and it will have these different files that have been downloaded. In particular, there's some information for being able to install the required dependencies. All the dependencies are over here in a file called requirements.txt. So let me cut back over to getting started on things. Let's see, getting set up, installation. So I'll put this URL into the chat. And this is from our documentation. There's a brief note here that shows about doing a git clone to install the software, and then once that's downloaded, connect into the directory that it creates. Once you do that, then you can do just simply pip install -r requirements.txt. So that's a typical way in Python to load up the dependencies, the different libraries that are used by kglab. If you are using conda instead of pip, then there's also instructions here for using conda to create an environment if you want, or add to an existing environment otherwise if you're familiar with using conda. But we've got environment.yaml, and then once you do that, you can say conda activate kglab. So you want to do one or the other. Probably wouldn't need to do both. The other thing is that if you don't have it installed already, we will be using Jupyter to walk through the different coding examples, different parts of the tutorial. So there's instructions here for installing Jupyter Lab, or if you use Conda, how to install Jupyter Lab off of Conda Forge. We've tried this out on a wide range of different systems, gotten a lot of feedback. I tried to make this as general as possible. So I'm personally using Mac and Ubuntu. I have two different laptops. The Ubuntu laptop is a K-Focus, and it's pretty much the same thing if you launch an Ubuntu instance in the cloud. It's very much like that. So I've been checking back and forth. I have other colleagues who've been checking this out on Windows. Hopefully this installer instruction will get you through depending on your operating system. And then once you're set up with Jupyter, Inside of that kglab directory, you can type Jupyter-lab and it'll launch Jupyter. So having said that, let me cut back and I'll pause sharing. And let me look through the comments to see if there's anything here in chat. Great question, McDonald. And yes, James, answer that. We will be recording this. Luis, I installed kglab dependencies via Conda. Yeah, good point, Luis. Yeah, I don't know quite what it is with Conda, but it takes longer to install through Conda than it does through PyPy, through pip. And it is a number of different libraries on which we're building. Certainly there's a number of them, and it's kind of the goal, is that we're trying to pull together a lot of different disparate parts and create a new abstraction layer that's like common ground between them, because there wasn't a whole lot of common ground before. So I will definitely, mea culpa, we've definitely tried to err on the side of including a lot of stuff. It is a pretty large build. I think, the saving grace is that with PyPy, you get a wheel, and so you can just sort of download the binary, is in some cases. But it sounds like so far this is going okay. If we are unable to install. Natalie, good question. Yes, if there's any problems with the installation, well, number one, let me know. We want to troubleshoot that. And especially if you can provide any kind of information on a GitHub issue, that'll help. But certainly you'll be able to follow along if you aren't able to install now. What I'm going to do is go through each of these different notebooks, each section in the tutorial. I'll be going through it line by line, and I'm going to show you, running all of these and talk through also, what's some of the background. So we'll be chasing some of the links that are included in the notebooks to show the context in the background before we execute the code. And then you have the code as well. If you want to, run this later, I really like to package these tutorials in notebooks, because then you can go back and kind of play what if, and if you change some of the parameters, what happens. I find that that's really helpful for learning some of these libraries. Again, we've tried to simplify the layer, the abstraction of how they're used. And so there's generally a lot going on behind the scenes when you're using different parts of kglab, and trying to change some of the parameters and see how it's different can be very instructive to learn. Yeah, Natalie, yes, that makes sense. Definitely, I run into that a lot in tutorials where, if you're at work, employers may have other policies about downloading code externally, or there may be security requirements on laptops, and some of that needs to be vetted. I know what you mean. Okay, great. Well, it sounds like we're getting through the installations. What I want to shift over to next is, let me unpause sharing and show just really where we're at. Here at this URL where we've got the tutorial, if I scroll back up to the top, there's a syllabus that describes the course we're in right now. So this is about kglab, and it's about integration of a lot of different libraries, NetworkX, PSL, pySHACL, RDFlib, PyVis, a whole bunch of different kinds of graph-based libraries. How do we make them speak more fluently with common data science tools like pandas and scikit-learn? But also, really, how do we also get these to use best practices for infrastructure and data engineering and MLOps? So making them so that they speak fluently with Parquet for fast serialization, so you can fit into Spark and Rapids, and also how to integrate with tools like Rapids so you can use GPUs. So that's a lot of the rhyme and reason about kglab, and we'll be reinforcing that with examples as we go through today. As I mentioned, the prereqs, really, if you can read 20 lines of Python, you're good to go. Definitely having some interest in knowledge graph is also a prereq here. If you have some of the math background, you may find parts of this more interesting. We're not going to rely on having a whole bunch of math here. We're going to talk more about just working on Python. But certainly there are some aspects where we get into areas of algebra, linear algebra, abstract algebra, topology, There's a lot of math going on behind the scenes here. So if that's an interest of yours and you have that background, it actually comes in really handy for making the code more efficient to run when you're working with knowledge graph and graph algorithms. And if you have any questions along those lines, definitely love to talk about it. The audience here, people who need to work with knowledge graphs, definitely Python developers, data scientists, data engineers, machine learning engineers. Also for people on the business side, the technical leaders who want hands-on implementation experience, executives who are interested in data strategy that leverages knowledge graph capabilities, and people who are interested in working with personal knowledge graphs. I know I talked with people in email yesterday after the meetup, and I know that there's a lot of interest in personal knowledge graph. And I'm going to show a few examples of that, but also some of the directions of where we're really heading on that too. The key takeaways we have, definitely how to work with open source in Python for building knowledge graph, but also giving you coding examples that are starting points that you can use in your own projects. And we do have a very active community around kglab. Our developers are very interested to hear more about your use cases. If there's something that can be done to customize or add features to support your use cases, we're all ears. So, these coding examples can be used as a starting point, but it's also just kind of a lingua franca for us to be able to talk together about what else you may need that we haven't, added here yet or integrated. A lot of what we'll be talking about, following on from the meetup presentation yesterday, is this notion of blending different approaches that are complementary. And I had a section in the talk yesterday about self-supervised learning, which is a way of saying if I have a complex object, I can train a supervised learning model on parts of the object and then use the model to attempt to predict the missing parts, the redacted parts, or ablated parts, if you will. So self-supervised learning is becoming a really interesting area of AI, particularly since it reduces some of the requirements of having to label all of your data. Instead, you can have machine learning help to develop the labels. This is really important in large graphs, working with graphs, because there's a lot of opportunities to work with complex objects. So it fits pretty well for self-supervised learning. But the other side of it too is that in enterprise, especially, you end up with these large graphs, your labels may not be correct, or they may be missing. So a lot of what we're going to talk about today are really, when you're building a graph, what are the techniques for building it, but then how do you start to test it? How do you start to do really some engineering thinking about, well, do I believe all of the annotations that are in my graph, and how can I test to find out the ones that maybe I think need closer review? So data quality checks, inference, different areas of being able to understand how, again, doing data science with graphs. As far as the outline, what we've had for the course, it really reflects the different notebooks that we have. And it's also, as you see over on the left-hand side, I'm clicking this this menu here. Basically, all of these different sections correspond to the notebooks that we have to show today, the different code samples, which basically just follow this outline. So we're going to go through a lot of different areas of graph. Don't really need to review that just yet. Okay, so that's what we're going to cover today. And let me check back now and see about if there's any questions. Also, I want to say, please feel free, ask questions at any point. I really love to catch a lot of the questions when we're in progress, because I think that provides a lot better context for everybody. So if you have any questions, let me know. And also, I'll say again, I said yesterday, but please feel free to link up on LinkedIn, reach out. I've already scheduled to talk with some of you folks about individual use cases. Great question. Okay, Sarah, want to know how to connect different ontologies in order to reuse existing ones. Fantastic. Actually, that's the first section we go through, is about how to reuse existing controlled vocabularies to build up the ontology you need. And then throughout the tutorial sections today, we'll show examples of how to extend those existing vocabularies to fit better with your use case. So we have a few examples of taking a couple of different, 2 or 3 or 4 different vocabularies that are well known, and then adding a little bit of OWL or a little bit of RDFS or SCAS or whatever to try to extend them for the use case at hand. Great question. Let me see if there's other questions too. Alrighty, great. Well, I'm going to cut back over to, yeah, great. I will unpause sharing. Let's see if there's another question. I will unpause sharing, and let me go back down here into, what I'm going to do now is, well, first off, clear my screen. Okay, so I'm going to say Jupyter Lab inside of the kglab directory, and this will launch Jupyter. Boom. And it should automatically redirect your browser and open up a tab. If not, the default is it'll be running on localhost :8888/lab. And when you launch Jupyter from the command line, it will give you instructions about how to open it up in a browser if that doesn't happen automatically. In some cases, depending on your environment, there may be a security key that's required. It'll also print that out, so you can just copy paste. But once you get there, you should have something that looks very much like this. You should see there's a launcher window, and on the left-hand side, we've got the directory, the kglab directory. We will be working mostly inside of a subdirectory called examples. So if you click down into examples, you'll see we've got a bunch of different notebooks, ex0_0, ex1_0, on and on. And these correspond to the different, actually they are what generate these different sections in the documentation. So the first part that I'm going to look at is under construction. Let me dig it up here. It's called data and ontology sources. And over in Jupyter, that would be ex0_0. So if you double click on that notebook, okay, we're bringing up the same thing. And just want to talk through the data that we'll be working with and some of the vocabularies we'll be working with. The tutorial is based on a progressive example, so we'll be reusing this data over and over and just kind of building on at every step of the way. So first off, the data is available under the DAT subdirectory. If you want to take a look at it inside of Jupyter, you back up to the top level, go to the DAT directory, and then inside of there, there's a number of different files. In particular, there's the food.com file. This is a lot of the raw data that we downloaded from a kglab data set, and it's linked over here, the same thing. Let me bring it up. There's a recipe aggregator called food.com, a lot of recipes online, and there's a file that's open on kglab of about 250,000 different recipes. And so we'll be using just a subset of this. And so we've done some preparation, but we'll be working with this file dat/recipes.csv. And if you click on that over on the left-hand side, it'll dig up. Okay, here's sort of the raw data that we have. And this is just a lot of recipes. This is a subset that we'll start out with. We'll use a bigger superset of this later on. But right now, this is about 250 recipes. And it's a CSV file. There's a few different columns. It's a little bit messy because the ingredients are all sort of glommed together into one column. So we'll have to split that out. But I definitely want to give a shout out to food.com for the recipes that they've published. One of them, a very simple recipe. I have some photos of my attempt at it, but it's called Anytime Crepes. And my family loves crepes. I love to make them. I use a slightly different recipe that involves using some beer, but kind of a family thing. But anyway, here is anytime crepes on food.com. And it's very simple. It just really has like 3 different ingredients, not that much. So to get started, let's see. If you notice on this recipe, sorry, anytime crepes right here. If you notice, it's the URL for this recipe is food.com/recipe/anytime crepes-327593. So there's an ID number for each one of these 250,000 recipes, ID 327593. There's some other metadata about this recipe. If you look, it shows that the preparation time is 8 minutes, and it's got the ingredients: egg, milk, and flour. And so for a very first step here, what we'd like to do is represent a number of these different recipes in a small knowledge graph. And so we're interested in how do we parse this CSV file and then convert it into RDF. So the first thing I'm going to do is up at the very top of the notebook, there's a small bit of administrivia, just so we get the paths all set up. And so always click the one at the top if you're running through the tutorial. And then I'll show just real quickly, here's here's a listing of the files in the data directory. We'll be working with recipes.csv. And let me click through a bit more. Okay, now we get to really the first line of code. We're going to import pandas. Pandas is PD. And then we're going to read a CSV file. Just very simple kind of thing to create a data frame in pandas. So definitely, data science 101 here. We're just going to load in that CSV file. We have it as a data frame now. And we can start manipulating it. So the first thing is, let's just break out these the ingredients. The ingredients were currently all kind of glommed together. So what we're going to do is break them out. We'll identify this one recipe in particular to explore. It's called Anytime Crepes, and we have its ID, and there's the different fields. And we're going to work on it as an example. Now, let me step back a bit and going to the question that I believe Sarah had. What we're going to work with is an ontology, a collection of different vocabularies. It's called food-on. It's really interesting. Food-on, I actually have a couple of friends who've worked on this project. Deborah McGinnis out of RPI, and some other folks out of UC Davis. There is an ontology, or actually a collection of ontologies that describes about food production, like going all the way back to talking about the different species of plants that are being used and harvested on a farm or orchard, and then going through, like in this case here, they've got apples. For what it's worth, I live on an apple orchard in Northern California. So near and dear to my heart, we've got an apple tree, and then we've got information about raw apples, and we've got information about recipes for apples, and then all of the food production steps going into making apple pie or canning sliced apples, etc. So food-on is really taking a look at our food chain and understanding all the way back from molecular biology, genomics of the plant species, on through what are the physiological effects of food allergies on different individuals, on through harvesting, production, yield, and then different forms of processing, food distribution, nutritional information, etc. Quite an interesting knowledge graph project. Now, inside of food-on, there's a couple of vocabularies that we're going to take a look at. One of them is a general description of types of foods. This is really more about a recipe. Let me load this up. And we're loading it up from Perl. It takes a while. And gosh, I hope Perl is doing okay. Yeah, it's not Perl, it's Get. Okay, I will load those up. I definitely want to show you the results. There we go. Okay, cool. So here's one of the ontologies inside of food-on, and this one is called What to Make. They abbreviate it WTM, but it's part of a knowledge graph, or it's a controlled vocabulary plus some data that's populated. about recipes that you can make and then studying those recipes. So there's a lot of different kind of information here. Some of it has to do with food allergies, flavors, but in particular, we're just looking at the real simple parts as far as modeling the ingredients and the cooking times. So we're going to be using this relationship, WTM has ingredient. And so here's some definitions of what is an ingredient. And there's a link out to Merriam-Webster, the definition of an ingredient, and a label and definition, and on and on and on. But that's basically what this vocabulary is giving us. There's another vocabulary over here that talks about sort of the individual's points or entities, data points that populate that knowledge graph of food on. And so, for instance, here we have all-purpose flour. Let's take a look at wheat. Let me dig up a few more. Whole grain, whole wheat flour. Okay, so for our anytime crepes recipe, it's got eggs, it's got milk, it's got wheat. All of those are populated here under this what to make recipe controlled vocabulary. So we're just going to reuse different ingredients out of here, and these will have a prefix IND. And oh, by the way, the format over here, it's a little bit weird. This is using RDF triples. It's not the easiest thing to read. It's got a lot of like HTML escaped characters. We're going to be using a slightly simpler version called Turtle, TTL. So basically what I was just showing over here in this sort of XML-ish kind of thing, it maps to what we'll be showing here in Turtle, basically the same thing. But the point I want to make is that we'll be working with, starting with these two different control vocabularies. One is about different types of ingredients, and one is about different types of relationships amongst food. And so each of these is called a namespace. So each vocabulary has a unique URL, and right here, and you can use that, the underlying software can use that URL to go out and look up definitions. And quite frankly, just what I did here, look up the URL, and then you can track down to what is the individual entity inside of there. And so that way, when you're working with knowledge graph software, you can make requests across the web to dig up metadata or other information about what's being represented in your graph. Now, a practice inside of RDFlib is that we'll shorten this URL and we'll have a prefix. It's just something that makes it a lot easier to work with. So for every unique URL, every vocabulary that we're going to use will have some unique prefix. And so in this case, we've got what to make, WTM, and IND for ingredients. And it really abbreviates things and makes it a lot simpler. And now, let's see, let me run this. Boom. So what I did was to just pull out that row from the data frame and then evaluate it. If you notice, the ingredients are listed as strings, and they're actually something that could be evaluated in Python. And once Python evaluates it, it turns it into a list. So here we've got a list that comes back and says the ingredients for anytime crepes, it's eggs, milk, and whole wheat flour. Now, respectively, when you map that back into the ingredient control vocabulary, IND, that becomes IND chicken egg, IND cow milk, and IND whole wheat flour. So we have 3 known entities that describe those ingredients. And the general idea there is you just mix and match a lot of these different controlled vocabularies to be able to represent what you need to represent. And if there's something that's missing, you can add to it. The way that we construct knowledge graphs when we're building up RDF, and also building up not just RDF, but our OWL and SCAs and other things on top of it, we add. It's a very additive kind of process. So we can start out by bringing in these 2 controlled vocabularies and bring in 4 or 5 or 6 others, add some of our own, add some data, analyze it, go back in, add some more relationships. We'll be doing that throughout the day. So I just want to stress that it makes it very convenient to mix and match. If you want more details about Foodon, it's called a farm-to-fork ontology. I highly recommend, here's some primary sources describing it. Actually, one of my friends, who I'm not sure, I think may even be here today, Charles Vardaman, out of Notre Dame, is lead author on ontology design for material transformation. So there's some great primary resources if you want to check out more about this. And in general, if you want to see what Foodon would do, like a full-blown thing, you know, a representation in a knowledge graph using Foodon, here's a recipe for banana, blueberry, almond muffins. And, you know, you've got a half dozen different ingredients, and you've got its recommended usage for different meals and courses, cooking time and temperature, serves for, on and on and on. So, you know, you can really build out on this notion of recipes. And the other thing I want to stress is, if you can do this for a cooking recipe, then, you know, you can use it for other kinds of recipes too, whether we're talking about industrial supply chain or drug discovery and pharma, you know, material science, on and on and on. There's a lot of places in the world where the idea of a recipe is sort of the problem at hand. And that's what we're trying to illustrate here. One last point. I just want to talk. We're using some data that is about food.com, and we're using this ontology out of Foodon. We'll be adding to it. I do want to point out that, you know, these are relatively large resources. I have taken a subset so that we can work with some very quick examples as we're starting out. So we'll be using sort of a medium-sized, non-trivial size that has about 300 nodes and 2,000 edges. So as far as the number of recipes is about, well, there's a certain number of recipes and then a certain number of ingredients that show up repeatedly in those recipes, but it comes out to 300 nodes about. And again, the intent there is I really just want to illustrate what's going on with the algorithms and the queries and the visualization. And, you know, it's overkill to use something larger. But realistically, we have source for, you know, taking this up a few more orders of magnitude. You know, definitely if you were just doing something raw with deep learning, you'd need like 10 to the 6 elements before deep learning really kicks in. These days, you can, you know, pull a lot of different deep learning models, especially for working with graph neural networks. You can pull them off the shelf and just retrain what's called transfer learning. So realistically, if you have, you know, 10 to the 5th, you're probably good. But when you want to run deep learning graph AI, you definitely want to work with more of a mid to large size graph. So 300 nodes is probably too small. 3,000 nodes, still a little bit small. 30,000 nodes would work pretty well with deep learning. And I also want to stress the point that, like, on contemporary laptops, you know, working with millions of nodes is not a problem. I've worked with cases in industry where, you know, we had 2-3 million nodes in a graph. I could run it on a laptop 5 years ago, it would run fine. Today's contemporary laptops are much better, especially if you have a GPU in them. Okay, so that's a lot of overview of at least where the data is coming from, where the vocabularies are coming from, and what we're going to try to do. So let me cut back over and I'll pause sharing for a moment and see. Okay, great. There's some questions. Okay, let me scroll back up and see what's going on here. Is not recognizable as an internal command? Mark, if you're running into that sounds like a command line interpreter might be catching something. Oh, in Windows. Okay, gotcha. Bharat, thank you. Okay, so it looks like there might be a Windows issue there, and I'll scroll down more and see. Yeah, so great question also from Luis and Brad. Yeah, the foodcom thing, the full data set, the CSV file that I was showing, you'd have to download it from kglab, and we didn't want to get into the licensing of redistributing that. But it is freely available on Kaggle. But what we did do is take a subset of it, and the subset is going to be in the directory under the git clone. That should be there, but not the full one. So I was just sort of showing that as background. And okay, right. So you've got recipes.csv, but you don't have the full food.com. Exactly. So yeah, that's what I was showing on Kaggle. If you really want to go back and look at the entire data set, it's available on Kaggle. It's not necessary for what we're doing here. And so I've taken a subset of it. And also just, I didn't want to get messed up in the licensing issues. Okay, Brett, great thing. Prefix.cc. Yes, absolutely. And we'll make mention of prefix.cc later on, working with prefixes and namespaces. But it's an excellent tool for being able to understand, well, what prefix should I use for this vocabulary that I want to import? Very, very much so, yes. Luis had a question, are there issues with the same entity or relation being defined in several vocabularies? Yeah, that's a good point. Definitely, this happens. Now, the thing is that when you're working with a controlled vocabulary and it has its unique URL or its unique prefix to describe as a placeholder for the URL, then, by definition, it's out in that namespace, that URL. So if something is defined, the same entity name, like whole wheat flour, is defined in two different vocabularies, ostensibly they have different URLs or different prefixes. And so they're differentiated that way. Now, trouble is you may have some vocabulary that imports and tries to redefine other vocabularies. I've seen that happen, in which case you might get some namespace conflicts. Just have to work that out. Generally speaking, it's not a good design to try to redefine somebody else's inside your namespace. But I've seen it happen. And, the well-defined vocabularies won't have that. James makes a good point about exact matches, same as. Yeah, so if you have things that are related, that are similar, like, maybe one vocabulary is talking about dried basil and another one is talking about dried basil leaves. So then you want to have ways of being able to define how similar are these things? Are they duplicates? Is one a subset of the other? And James is making a really good point. There's a standard called SCAS that's used for developing taxonomies to really describe is something a broader case or a narrower case or an exact match or same as, different flavors of relationship in terms of taxonomy. And that's very, very important, especially as you start to mix and match from different sources. Maybe we're bringing in some data sources from food.com, other sources from USDA, on and on, and they may not perfectly align on their definitions, but you can go back and use some SCAs to tie them together. There are other techniques for this as well. And it's especially useful if you've got an industrial application where there's a lot of different vendors and different parts catalogs, trying to understand which parts could be substituted for each other. It's important. If you're building aircraft, it's really important. So yeah, this is a big issue as far as managing knowledge graph. All right, exact match. Yeah, we'll show a little bit of SCAs later on. Very, very good. Excellent discussion on that. Any other questions so far? We're just kind of getting started. Let's see. Okay, and also, Sarah, you had the question earlier about like how do we mix and match ontology or parts of ontology. We'll be diving into this much more. I've just shown 2 so far. As we develop this example, we'll probably be using about 12 different vocabularies. Okay, great. Let me go back to, sure, unpause. All right, and now I'm going to go back into the examples directory. Come on, there we go. And let's see. I'll click out of whatever. I'll leave that notebook, but let me go to EX10. And okay, So EX10. So what we're going to do here is start to build a graph using RDF. And in Python, there's a really excellent library, or I personally think it's excellent. It's called RDFlib. And let me... And you won't need to use this for these examples, but the documentation is online, rdflib.readthedocs.io. And a lot of what we're doing is built around RDF as kind of a foundation, at least for one part of kglab. So RDF, I will say it has kind of everything but the kitchen sink. You know, it handles serialization, it handles Sparkle, it handles some inference. There's a lot of things you can do. But then there's other plugins. There's other libraries that are built on top of this. So for instance, we'll be using pySHACL, which is built on top of RDFlib to do SHACL implementation. There's some pretty good documentation. It's not my favorite documentation of an open source project in the world. I find that RDFlib docs are kind of written for people who are already experts in RDFlib. So we try to work around that, and everything that we have in kglab, you may have noticed, but you may have noticed, but we have a lot of wrappers around whatever we're calling. And then let me flip this back up. I should mention that if you go to kglab docs, over on the left-hand side, there's a list here of the different sections. One of them is called technical reference, and we've got the package reference underneath that. And if you click that, it's got the API docs for all the different parts of kglab. And anywhere that we're wrapping some other library, like for instance, RDFlib, we'll describe how we're wrapping it, which parameters we're using, what defaults there are, and just give a little bit more background. So, you know, not to get too pedagogical, but the way that we're building the docs is from the perspective of somebody who's beginning, who's trying to learn this, and doesn't understand, you know, expertise about working with individual libraries already, but is really approaching it more from a conceptual level, and then trying to get hands-on experience. That's how our docs are built. A lot of these libraries are sort of just, we're the developers, and we're gonna document what we implemented. So it's from an expert perspective. So we're trying to backfill. That's what I'm saying. All right. Having said that, I'm over in EX10, and we'll just, our magic line at the top to set up the paths, we'll get that first. Okay, we'll say import RDFlib. What I'm going to show is how to build a graph, a small graph, sort of in the raw, just simply using RDFlib. We'll do that, and then we'll show doing the same thing with kglab. So we'll show a contrast of hopefully how we make this simpler. So first off, import RDFlib, and then we instantiate a graph object, which will be the variable g. Should be quick. It's a blank graph. And now working in RDF, there's a concept of how do you make a statement? And so every statement is sort of this grammatical construct. It's called a triple, or at least the base case of it is a triple. But you've got three parts that are really important. There's the subject, which is the entity that you're talking about. There's a predicate, which is a relationship between the subject and something else. And then there's an object, and the object is what, you know, the subject is relating to. It could be some other node, some other entity in the graph. It could be a literal value. So, you know, you might say that anytime crepes as an entity is our subject, and the predicate is cooking time. And then the object might be a literal value, 8 minutes. So by building a graph, the interesting thing is, you know, a graph is composed out of nodes and edges, vertices and arcs, however you want to describe it. I'll typically talk about nodes and edges. But by having this construction of a triple, a subject, predicate, object, you can build very complex graphs. But then at the same time, it's really just a collection of subject, predicate, object. So there's a couple of different ways to think of a graph, how to construct it, also how to iterate through it. And so when we're representing here, starting to build our graph, anytime crepes, let's take the URL for anytime crepes, which was what we have right here. And that's www.food.com, etc. And we've got the ID. And then we're going to wrap it with an RDFlib call. We're going to create something called a URI ref, and that will give us a subject node. So you can see what comes back in RDFlib is this object in Python, and that will be what we'll use for a subject. That's an entity we've created out of the blue. And we're going to think about this as something called a persistent identifier. In this namespace from food.com, they've got unique identifiers for all the recipes, these codes here, 327593. So that's just going to be a kind of identifier that we'll have for this anytime create recipe, you know, from henceforth, we'll use that to reference this recipe. And there's a broader concept called persistent identifiers, where if you're talking about somebody's paper, there might be a DOI identifier where anywhere in the world we can give you a URL pointer for this paper, even if they shift publish, you know, they move to republish in a different journal, we'll just do a URL to redirect. Or another kind of persistent identifier might be, if you're a researcher, you probably have an ORCID identifier. I have one. So for anybody doing research, you can look up their ORCID ID, and then we can, you know, put their information into a graph and identify different people. Talking about books, there's ISBNs, journals, there's ISSNs. There's a lot of notion of identifiers, but those typically are something that are unique and persistent for the sake of subjects. Another thing that we'll be doing is building out relationships in the graph. So the first predicate we'll introduce here is, it comes out of RDF. It's called RDF.type. And it's a way, think of like inheritance in object-oriented programming. We're going to say that our first recipe is of type WMT recipe. So going back to the food on ontology, we'll say WMT colon recipe, and we'll say that our subject there, we're going to build it out of that type. You see what comes back here. This is a long reference going back into the RDF space, the RDF namespace, where you can start to define sort of class hierarchies. Okay, the next thing I'm going to do is in RDFlib, there's something called a namespace manager. It's a little difficult, I find, to use, not quite intuitive, but basically we're going to create this object, and then we can add URLs to create namespaces, add prefixes, etc. And as mentioned, Brad made an excellent suggestion. There's something called prefix.cc. If you go to prefix, WMT, let's see what we got here. Ah, nothing. Okay. Let's try something else. Discuss. So there's a lookup here, and what this provides is a custom search, if you will, to be able to look up these different kinds of vocabularies. What is their unique canonical URL that's being used? In some cases, there may be some alternatives. Also, what is the prefix that's being used? In this case, scas. It's a really super helpful resource, because coming back here, these prefixes like RDF and WTM and IND, they're conventions, and you hope that you use them consistently within your knowledge graph, within your instance of your knowledge graph. If you don't use them consistently, RDFlib will scream and throw errors at you. But there's no guarantee that the conventions that you use are going to be something that another person uses for the exact same namespace. So using a tool like prefix.cc is a way for people sort of to align on what names they're going to be using. All right, so let's go and create a definition of this WTM one out of foodon. And so we'll get the URL for it, and we'll create a URI in RDFlib, and then we'll bind that inside the namespace manager. Boom. Okay, and so now the fun thing is that looking back here at the the WTM ontology, there's these different components in it. But because we've created a namespace, all we have to do now is just say namespace dot and whatever the name of the component is, and we will automatically be referencing that entity off in that other remote namespace. So we'll do that here. And we'll call the recipe kind of entity. And so now we can create a triple We're going to add to our graph, which so far was blank. We've got the subject, which is anytime crepe. We've got a predicate, which is RDF type. And then we've got an object, which is WTM recipe. So we've created our first triple, really the first part of the graph. And now let's add to it. There's another kind of predicate, has cook time. So we'll the predicate there, and then we'll import another namespace. This is called XSD, and it's a way of defining units for, well, it's a way of defining a lot of metadata for different types of literals is one of the things that it provides. So here we've got a number 8, which is, we're going to just represent that as an integer. What it means is 8 minutes cooking time. And so to make sure of that, we're going to say, okay, this is 8 as a string. By that we mean it's an integer, and it has a predicate, has cook time, and we're going to assume that that's in minutes. There's better ways to do this, but this is a simple case. So we added it to the graph, and then we're going to take and go back to WTM and use another predicate called has ingredient, and start to build these out. So here's an ingredient for chicken egg, boom. And now we can add that triple into the graph to say one of the ingredients for anytime crepe is eggs. And then we'll do the same for milk and flour. And now to confirm what we've built, we'll iterate through these triples out of the graph. So G is the graph in RDFlib. And so SPO is the subject, predicate, object. And we'll print each one of those. And so our graph internally is basically these triples, these half dozen triples here that talk about, hey, it's a recipe, it has a cook time, and it has 3 ingredients. Okay, so that's a roundabout way of saying if you're working with raw RDF, especially in RDFlib, there's a lot of steps. Let's try this differently. Oh, by the way, before I go to that, let me show how do you save this using RDFlib. So we talk about serializing out a graph. We'll use different formats. In this case, we'll use TTL, which is turtle. It's sort of the simplified view of RDF. So what I'll do is I'll serialize it and just print out the string. You can see here, I've got the prefixes and namespaces up the top, and then I've got one entity, which is our recipe. And then I've got, hey, it is a recipe, it's got a cook time, it's got 3 ingredients. So that's our graph. That's what you'd save in a file. And similarly, if you want to just store it directly to a file, boom, we'll do that. And then suddenly you should have a file that was just generated, same thing. Alternatively, there's another format called JSON-LD, which will linked data version of JSON. So I'll write that out, and then it will create this temp JSON-LD file. Same information, formatted as a JSON file. It's a little bit easier for machine readable applications because frankly, you have to have some sort of special parser to be able to read turtle, but so many different languages support reading JSON files. So if you want to take and serialize out your graph and then read it in a web app, JSON-LD is pretty good. Ergo, Google's been pushing this, having JSON-LD inside of web pages for search engine optimization. One of the things about JSON-LD, though, is they have this notion of a context. So they're going to want to have some metadata about your graph. They're going to want to enumerate all the different prefixes and namespaces for your vocabularies. They're going to want to know things like what language is it in. So we'll just create a dictionary in Python, and then there's your context. So when you serialize out, boom. Now if I dig up the JSON file, it should have, now if I dig up the JSON file, it should have that information. Yeah, okay, so it's got the context, the language, etc. A little bit more readable that way. Okay, that's the hard way to do it. And now what I want to do is cut over real quick into showing how to do this in kglab. So up at the top, our magic path correction. And then what we'll do is we'll import kglab as a library, and we'll create a dictionary of our namespaces, kind of the context thing. And then we'll create an object that's called a knowledge graph out of kglab, and we'll tell it, hey, you're going to be a recipe knowledge graph based on food com, and you've got some namespaces. And that will create a variable that we'll work with henceforth called kg. Boom. So, okay, that should happen pretty quick. Once you've got that kg object, you could call it anything. It's just a variable, but we're going to call it kg. Now we've got a lot of shortcuts. And so now if we want to go back in and do all of the above, all we have to do is say, well, you know, I want RDFlib because I'm going to use some literals. I'm going to create some nodes for our graph. So I'm going to create the recipe node, and then I'm going to go in and add to the kg object. I'm going to say, take that recipe node, and I'm going to look up the namespace for RDF, use an RDF type, and I'm going to look up the namespace for WTM, use WTM recipe. I'm going to add that to the graph. Then I'm going to add the cooking time. And in this case, get a little bit more fancy. We're going to say the literal, instead of just 8 as an integer, we're going to use a duration kind of way of representing literals in XSD. We're going to say this is a time of 8 minutes. And we have a formal way of looking at that and making it machine interpretable. And then we've got the different ingredients too. So basically, by using kglab, we're able to, you know, just use a half dozen lines of Python, and boom, you should have your graph. Let's iterate through it. So, you know, the same thing that we had before. Hopefully, it's a lot less steps. Now, if you want to serialize, let's go back over that again too. Same thing. It's just, you know, much simpler way to do this. Also, we fixed some bugs, and we've tried to make the serialization routines much more reliable. So that's one benefit. We'll save it in some different formats. If you want, you could save it as XML. So let me dig that up. Here's the same thing in XML. Saving it as JSON-LD, etc. And the point that I want to make there is that what we're representing, the data and the metadata, the graph relations, in all these different serialization formats, and really there's like a dozen of them, they're pretty much representing all the same information. And with a couple of lines of Python, you can read and write, you can convert from one to the other. So there's nothing particularly sacred about any one of these representations. Some have a few extra features in them, like quads, but in general, if you're just talking about representing triples, you can go back and forth very simply. So there's a lot of, I've heard, you know, culture wars between like JSON-LD versus Turtle. None of that. 2 lines of Python, you can go back and forth. But the thing that's not represented in RDFlib is something called Parquet. And so I'll represent this. In Parquet, it's used a lot in big data. It's called columnar storage. And it's much, much more efficient for handling a lot of data. It turns out Parquet is super efficient for handling graphs. And it also makes it so that you can use tools like DataStax or Databricks, Rapids, a lot of the kinds of big data and data science tools that expect Parquet format. If we store it that way coming out of kglab, it's a lot easier to use with the other tools. Also, it's an order of magnitude faster and smaller. So there's just really, you can store more metadata with Parquet as well. So this is a very, very small graph. It's not going to show it. Actually here, there's some overhead. Parquet turns up, it looks larger in this instance because we just have one entity. But once you get into a larger graph, the numbers here shift dramatically. Parquet becomes much faster and much smaller. Okay, I've spent a lot of time in these first 2 notebooks because I really wanted to cover some of the basics. Actually, the first 3 were notebooks. I'm going to go at a much faster pace moving forward, but let me check back here and see if there are any problems. What ontology would you recommend for using? Oh, good. Okay. So Sarah has a question. What ontology to represent units? Great question. So they're inside of XSD. There's a lot of units that are being represented, although there are others, really depending on the kind of application, because it can be somewhat application specific. Certainly, okay, great. Thank you, Bharat. UCOM is another one. Actually, let's look that up and see. So for instance, if somebody tells you that there's an interesting one, okay, great. There's UCOM, and then let's go look that one up. Let's go directly to it. That's what's really nice about working with these controlled vocabularies is, generally speaking, they're URLs. they're web pages. Not exactly, but they can look as if they're web pages. That gets into a lot more internals of REST and representation. But you know, the thing is, you can go out and browse them and see what's in there. This is coming off of Perl. Well, a lot of these vocabularies are on a particular. I think it's on the same site. Anyway, taking a while to load, but we'll see what's going on there. Let me go back to other questions. Luis, no module names Qdif. Interesting. Well, okay. Well, let me go back to the question. QDT, sorry, QUDT. Yeah, I'm not familiar with QUDT. I'll look up that one too. And then, Luis, you have a question about QDF. And as far as how the library is set up, you shouldn't be seeing that. So that's a bug if it's showing up. Is anybody else having the problem with CUDF? Because the way we've wrapped it is if you don't have GPUs, that's not a problem. It should fail over and instead just be using Python, vanilla Python. Let me take a look and see. GPU count. Yeah, that's wrapped though. Interesting. Okay, so it's throwing an exception. Wow. Okay, well, we've been testing this in a lot of places, and there's a that's in the util part. Interesting. Okay, I'll have to dig down and start to reproduce this one. Thank you very much, Luis, for reporting that. Oh, but you are running with NVIDIA GPU. Oh, I get it. I get it. Okay, yeah. My apologies. I need more coffee. Oh, really. Yeah. So what we're doing under the hood here is there's a number of libraries that NVIDIA provides, open source. There's QDF, which is a GPU optimized version of pandas. There's QML, which is a GPU optimized scikit-learn. There's kglab, which is GPU optimized NetworkX. We've actually been working with NVIDIA. They're one of our clients. And working with the leads, some of whom have been checking out kglab, but they've helped us out. So yeah, actually what we do is we detect, if you have GPUs, we go in and detect that, and then just make the assumption that you had those Rapids libraries installed, and that's not a good assumption. So my apologies, Luis. If you're working with Conda, it's real simple to install QDF, and I can help out on that. But I thank you for finding that. I'll need to wrap that better. If there's a way, if this is causing problems for you, if there's a way on your system to turn off your GPU, I know that like on my laptop, I can do that very quickly. That might be probably the best workaround. And anybody else, if you're seeing any problems with installations or GPUs, yeah, okay, turn it off. That sounds good. Great. Okay, first hour in, we took a long time to talk about namespaces and setting up graphs, and it's kind of the basics of serialization and RDF. This will be foundational. We'll be using this over and over throughout the day. I really wanted to spend time on that. Let me pick up the pace a little bit and start showing some applications of what we're doing here. So I'm gonna take this down. I'm gonna clear out a few files here. Yeah, okay, great. And now I'm gonna go to EX20, load that up. Okay, and so what we're gonna do is go back into our recipes.csv file, and we're gonna create a graph that doesn't just have one entity, it has a number of entities, about 300. So first line, and then we'll come in here, we'll create a graph.
Just a quick one, Paco, you're paused in presenting.
Oh, very, very sorry, very, very sorry.
No worries.
Okay, great. Sorry, let me back up a bit. I just loaded EX20. I'll load this notebook, and I'm gonna run, again, the top set of the paths, and then I'm going to go back in, same thing again. I'm going to import kglab, and I'm going to create a namespace, a set of namespaces. This time I'm adding another one called scars that allows you to build taxonomies. We'll use it for a little bit here, and we'll create a knowledge graph object. Boom. And just for kicks, if you ever want to see what you've got loaded up into let me restart this. For some reason, this one is not. Sometimes in Jupyter, you may have to restart things. So let me restart this kernel and rerun, because it just wasn't responding. Okay, great. That's better. Sometimes it gets stuck. Jupyter's like that. I've created this object. Sometimes it's interesting if you pull together a lot of different vocabularies just to print out what you've got. So we've got describe.ns, describe_ns, and that'll just give you back a data frame that gives you all the prefixes and the namespaces. So by default, there's some of these namespaces that are foundational. You use them over and over again. RDF, RDFS, schema, XSD, OWL, prov, DCT. These are just basic things that are used over and over so often. We include them by default. If you want, you can tear them out. There's ways to get rid of that, but we do include them by default. They shouldn't be any problem if you don't invoke them. Okay, now what I'm going to do is come back here and create a dictionary that says for certain types of key phrases, I'm going to map those to known ingredients out of our IND vocabulary. And it's not a lot of them. There's a couple dozen, but common ingredients in recipes. And the idea here is what we're going to do is just extract out the recipes that have these ingredients represented. So we're going to work with a medium-sized graph this way, not a ginormous huge graph. But it'll be a way of converting from a CSV file into a graph. Okay, and so now what I'm going to do is, again, create a pandas data frame from recipes.csv. And then I'm going to come in and iterate through, take a look at all the different rows in that data frame. And for each one, I'm going to look up what are the ingredients and then add them into the graph. For each recipe, we add it into the graph, but then we're going to look up and see for each ingredient, we're going to add that ingredient into the graph. We're also going to add in a literal to describe a SCOS definition. You'll see this in a moment, but basically taking the string title of the recipe and creating that as a SCOS definition. We're going to format out in minutes what is the cook time. So basically, this is a way of ingesting a CSV file and coming up with an RDF graph. Boom. And now, okay, let's visualize that. So we'll cover visualization a little bit later. This is just a few lines of Python to say, I'm going to take my object, my KG object, and I'm going to create a tensor out of it. I'm going to represent it as a different kind of algebraic object. And then I'm going to use that to populate PyVis. So a couple of lines of Python, and I'm going to create an interactive visualization. Boom. Okay, and so that generates some Python, some HTML and some JavaScript. As you'll see, it's loading here. So I've got about 250 different recipes, or some set of recipes, I should say. Okay, great. So here's an interactive representation. The orange thing at the middle of this graph is the notion of a recipe. So in terms of ontology, the recipe is the most central thing, right? Because we're representing a lot of different recipes. But kinds of recipes, that's interesting. So the light blue dots, let's see if it works. Those are different individual recipes. The dark blue dots are ingredients. And the thing that this visualization shows is that the most commonly used ingredients are going to show up as more central. They're going to be closer to the core of the definitions. So if you look at the grouping here, this cluster of dark blue dots, you'll see salt, flour, butter, and milk. You can make a lot of things with salt, butter, flour, and milk. And then moving out a little bit, we'll add some water, or maybe we'll add some sugar. Moving further out, we've got some olive oil, and we've got garlic, and we've got things that don't show up in every recipe. So that's kind of a representation then of, like I say, 250 recipes and really a couple dozen ingredients. How do they all fit together in a graph? And you can see the relationships between them. If I were to take honey and pull it, I can stretch it out here, and all of the different recipes that we have represented in this graph that use honey, they start to track along. Okay, so just interesting kind of representation. Another thing, while we're here, we've just ingested sort of a medium-sized graph. Actually, it's pretty small, but we'll call it medium-sized. I want to show a little bit about comparing performance of serialization, because when you're working with graphs at scale, this is actually a really important matter. So what I'm going to do is import the time library, and we're going to have a way of saving off a file and then figuring out how much time did it take to save that file in that format. So I just did turtle file, and now I'm going to save also as XML, JSON LD, and then Parquet. Boom. And now let's take a look at that. Okay, great. And so what this is showing is that the same exact graph represented 4 different ways. You can see that XML is pretty large, and we know about that. And you know, it takes a while. Turtle is actually fairly readable, fairly compact, but it's kind of slow to write. JSON LD somewhere in the middle. But what's interesting here is you get order of magnitude reduction in file size with Parquet. And the write time is also much better than Turtle. And frankly, the interesting thing about Parquet is it has to load on its first invocation. So if I go back here and rerun these, boom, boom, you'll note that the write time for Parquet drops dramatically. It cut more than in half by 50%, because some of that overhead has been accounted for already. So with Parquet, it's really good for doing sharding and like taking a large data set and cutting it up into different partitions, and then serializing those partitions in parallel. And because of that, you get these write times that are just much, much lower. File sizes overall are much lower. There are other techniques such as predicate pushdown, which, you know, basically when you go to query, there's a lot of optimizations. There's compression that's built in, et cetera, et cetera. So Parquet is turning out to be much, much better for graphs, although it's not a default built-in thing. Okay, so that is building up a graph. And then let me cut over to, I'm going to go to EX30, and we'll dig into a little bit more about visualizing a graph. So I'm going to back up a bit and show what we did with PyVis. There's a library called PyVis, and what it does is to generate HTML and JavaScript so that you can visualize interactively with a graph. I'm going to use PyVis in the raw first, just to show what it's like and how to drill down to it. And then I'll show it wrapped up in kglab. So here I'm going to create a very, very simple graph, just 3 elements and some relations between them, and put this raw into PyVis. Boom. And that should create, yeah, just this very, very simple graph here. So we've got foo, bar, and bars, and then some relationships between them, foo, bar, and x, y, z, z, y. Now, let's do the same thing using kglab. Actually, we'll use a larger graph. So what we're doing is I'm going to take and load one of those files that we had saved off in the last notebook. Actually, it's really interesting if I dig up temp.ttl, turtle, here's the graph that we've been working with in turtle representation. And you can see the different recipes. You can see, like, here's one for Astoria frosting. Here's one for simple popovers. And for each one, you've got its duration, you've got its ingredients, and its label, on and on and on. So let's take this graph that we have and visualize it again. Again, it's real simple, just a couple of lines of Python. We're going to convert from our graph into what we call a subgraph. So we're basically converting it into a tensor, like a matrix. And then we use that to build out PyVis. I'm also going to throw in one other part. We have a style object. So for each one of the namespaces, they're optionally, if you want, it's not needed, but optionally for each different prefix, each namespace, for the relations in that prefix, you can give it some styling, some design. So in this case, the WTM vocabulary will be colored in orange, give it size 40, and then the ingredients will be colored in blue and give it size 30. And when I run that, boom. Okay, now I've created a PyVis graph, and then I'm going to render it interactively here in the browser. So in visualization, there's different types of dynamic visualization. In this case, we're using something called Force Atlas 2, and we'll save it off to an HTML file so we can dig it up later, but those lines will render it. And this will be the same thing we looked at before, but I'm just trying to break down what were those elements, how did they get there? All we had to do was just say, well, you know, if you've got an ingredient, it's coming from a particular vocabulary, we're going to have that in dark blue. If you've got a class of a food kind of thing, like a recipe, that's a little bit larger and it's in orange. And everything else is just defaulting out to a light blue. So you can really go through this in much more detail. Oh, by the way, there's also, you know, zoom and drag. If you zoom out to a far enough level, you'll see all the labels. It's kind of noisy though. But the nice thing is, when you create a visualization with PyVis, you can literally just save it off as an HTML file. And that's the file that we called it was tempfig3. And if you dig that up over here, okay, great. We've got some HTML. You could take that and put it into a web app. You could put it into a standalone page. You know, you can embed it in a lot of types of applications. It'll take a little bit while to render it there. But, okay, so that now we're working with a larger graph. A little bit of an introduction to some tools for visualization. Let me cut back over and see. Let me pause sharing and see if there's any questions. Oh, great. Okay, good. And so, Brett, you had a good question there. JSON-LD was fastest, and then the second time around, Parquet was faster. Yeah, so what's interesting there is what Parquet does is something called a dictionary compression, or at least by default. You kind of got to dig into the way that we're using it is we call pandas, pandas calls arrow, arrow calls Parquet. And if you're using rapids with GPUs, there's another couple of libraries that get in there in between. But what happens is that when you've got a graph that's represented as subject, object, predicate, and maybe some other information too, you've got all those triples. Basically, you've got a big column or storage for the graph. So you've got 3 columns or more if there's some other metadata, but then you've got a row for every triple. What Parquet does is to use, in this case, dictionary compression, which says that for each column, I'm going to look at all the different instances of strings that show up in that column, and I'm going to map them to numbers, and I'm going to compress them based off of that dictionary. And so that's really cool for working with RDF graphs because, you know, the predicates, we'll look at this later, but the predicates, there's not that many of them. So far, we've only used like a half dozen different predicates. I could have 1 million different entries in the graph, maybe only a dozen different predicates. And so that column can just, blam, be compressed into a very small space. And similarly with the entities, you're going to make a lot of links and references amongst the entities. There's probably many more links than there are actual entities. So you're going to see the subjects and the predicates being repeated many, many, many times. Similarly, when you take the full URL, then Parquet will put those in a dictionary, boom, compress them. So what happens is you get this overhead the first time you do it, you're building up your dictionaries and also loading some of the libraries. But when you see subsequent runs of Parquet, they'll be a lot faster. And Sarah, good question. Is there more human readable visualization to see the superior structure and not only the instances that are connected? Very good question. Yeah, so good question, Sarah. What you could do there, another thing you can do is to query the graph first and then visualize the results of the query. So you may want to pull out, as you're saying, some of the superstructure. Another word for that is what's called a backbone. And you'll hear the term multi-scale backbone, for instance, being used. So you might want to use a Sparkle query and pull out the parts of the graph that you're really interested in visualizing and consider that to be your subgraph and then visualize that. We'll show some examples of that a little bit later on. And then Brett, does Parquet help with two-way relationships between concepts, if that makes sense? Often you build it one way, then forget the other way. Yeah, that's great. Okay, thanks, Sarah. Yeah, Brett, that great question. When you're representing relationships between different kinds of entities, it may be bijective. And That's a mathematical term, and I can get in real trouble because the mathematicians have very nuanced ideas about bijectivity. But let's just say that let's just say that you've got some kind of relationship. It can go in either direction. So you know, if I were going back to my Viking example that I mentioned earlier, you know, Life is son of Eric, but then Eric is parent of Life. And when you're working with RDFS and OWL and constructing these kinds of relationships, you will have inverse relationships that can be automatically mapped. And the nice thing about working with RDF graphs is you don't have to specify those explicitly. You can use something called inference, which will show where you fill those in. And typically, if you're going to be doing some analysis of a graph, you know, such as doing SHACL, applying SHACL rules, you'll want to run that inference first to sort of populate out all the missing parts. That's generally called inference. OWL closures is another name for that. But it's how you fill in those two-way relationships. Even if they're not explicitly known, if you have one half of the relationship, you can infer the other half. Really good question. Okay, great. We're an hour and a half in. James, should we take a bio break? Give people maybe 5 minutes to take a break? Sorry.
Yeah, yeah, sure. Go for it. Yeah, so there's half an hour left, and because there's back-to-back session, I'll need to leave probably to get ready for that. But sure.
Oh,
yeah.
Oh, wait, we have a half hour left. Oh, I was thinking it was longer. Sorry. In that case, if we've only got a half hour left, we're only going to 11 Pacific, so it's a 2-hour masterclass, right?
Yeah, yeah.
Okay. In that case, since it's the shorter time, let's not do the break. We'll go through this a lot quicker. There's definitely more things we want to cover, some questions. So let me jump in. I'm going to go back and let me share. Unpause sharing. Okay. So we were just talking about queries. I'm going to load up EX4, and we'll go through this real quick, but very simple to do queries. Do the magic path thing first. There's something called SPARQL, which is a standard query language for RDF. There's other kinds of querying of graphs, but SPARQL is very, very popular. So what I'm going to do is define a different graph. This one here has 3 people, and we're using a vocabulary called friend of a friend, FOAF. Okay, and now we'll just bring this into, we'll create an RDFlib. We're going to show how to do this in raw RDFlib first, and we'll show how to do it in kglab. So I'm going to define a query that says I'm going to look for a person and their surname and their email. I'm going to do that by finding triples that match these 2 patterns. I've got a person, they've got a FOAF, a friend of a friend, family name is a relationship and a particular surname. And then they've got an inbox, which is a relationship for an email address. So basically by filling in, substituting the variables here, these 2 relationships are a kind of shape in the graph that I'm looking at through the SPARQL query. I'm going to find all the instances that match and then collect out these variables up here, person, surname, and email. Also, I'm going to sort them in order descending. So that's very similar to SQL queries if you use these before. It's a little bit more complicated. There's a few different kinds of things we added, but it's similar. So I'll take an RDFlib graph, and I'll call query with SPARQL query. And then I'm just going to iterate out and show as each row in the result set as a dictionary. Great. And as you can see, here's email, person, surname that's being matched. Patel, O'Neill, Nakamoto. And if I want, I could populate this a little bit more. I could take and convert some of these different literals into something that's a little bit more of a Python data structure. Great. Now, let's show doing the same thing, though, with kglab. So here, got a graph I'm going to define using my fragment before of 3 friends. And, oh, sorry, I'm actually going to use my food graph. Sorry, a mental slip there. I'm loading up my temp.ttl, the recipes database that we'd shown before. And now I'm gonna query it. And instead of asking for person, surname, and email, I'm going to ask for recipe, and then definition of the recipe, the label, and the cooking time. But it's very similar. We're keying off recipe and its relationship as recipe RDF type, and then for recipe, what's its SCOS definition, and then what are the ingredients and cook time. And again, sort descending by time. Okay, so that's just a string, but that's our query. And here, what I'm going to do is I'm importing pandas because I want to visualize this. I'm going to call our kg variable, our knowledge graph. I'm going to say query as df, data frame, with that sparkle string. And what I'm going to get back is a data frame representing the results. I'll just show the top 20. So this is a convenience. The result set is coming back as a data frame, which means I can go and operate on that with scikit-learn or something else that expects data frames. You can see the formatting there. We've got recipe, duration, and time. Now, it's interesting looking at these. You know, most of these recipes that are coming back in the query, they're like an hour and a half long, right? They're typically baking cookies will take you an hour and a half. Some of these things, though, are taking a lot longer. Here's eggnog takes 1 day and 30 minutes. So that's interesting. There's definitely a lot of distribution when it comes to, we'll use that a little bit later on. Okay, so let's do some post-processing from the queries. So again, we've got our recipes, and in this case, I'm going to go to a slightly different file. It's under dat, and here, what we've done is to add a bit more taxonomy. So we've got this notion from SCOS that we're going to start to define some things that are done to recipes. So I've got a concept of process, food processing, and you'll notice that we're linking out to some other resources. Here we're using DCT vocabulary identifier to link out to Wikidata. And here's a food processing webpage on Wikidata. Here is mixing as a type of food processing. And there's a SCOS closer match out to food on, talking about mixing and blending as a type of food process. So we're using a little bit more sophisticated use of the food on ontology. Kneading is something in contrast to mixing. So if you're making bread, you're kneading. If you're making crepes, you're mixing. And here we've got RDFS, where we're defining a bit of a relationship in terms of describing food processing. And we're going to use this then to say, let's start to look at our food recipes as kinds of dishes that we're preparing. And some of these are based off of creating dough and kneading the dough. And then some of them are based off of creating a batter and then mixing the batter. And in particular, we have some instances, we've got pancakes like crepes, or we've got noodles like dumplings. And that was something I noticed when I was looking at the recipes, because some of these, the dumplings take like 2 days to prepare. Some of the Eastern European recipes are pretty interesting that way. So what we're doing is basically taking, this is like an additional components of vocabulary that we're creating on the fly by reusing OWL and SCOS and other things. And now we're going to add that in to what we had from our recipes. So what we're saying is we've loaded up what we had before, but now in addition, we're going to do this additive thing and load up nom.ttl. And so it's just added into there. And now when we start to do the Sparkle query, let's take a look at some results. We'll do some post-processing. So again, we're going to try to go after recipes that have egg, flour, and salt, as we saw in crepes. But there's a lot of different kinds of recipes that combine those 3 ingredients. So here, let's tally them up. And so what's interesting is that when you look at these, most of the recipes that have eggs, flour, and salt they're going to be either some type of pasta or some type of noodle or some type of bread, some type of batter. And we're going to take a look at inside of the names. We're going to do a little bit of lightweight text analysis and say, hey, if it says noodle in the description, we'll call it that. If it says dumpling, it says spätzle in German or pasta in Italian, we'll call it that. We'll say that it's a type of noodle. But we'll also take a look and see, does that recipe have an additional ingredient of butter? And this is interesting because now we can start to apply some rules on top of our SPARQL query. Okay, and we'll tally these up. And looking at this, I'm going to use a mosaic plot, but we build up a table that says, it turns out there's a conditional probability of it says it's a noodle and it has butter in the recipe versus it has butter or it says that it's a noodle. Long story short, what we're going to do is come up with a simple rule to try to differentiate. Are we working with a kind of noodle or are we working with a kind of pancake? Now, there's other types of recipes. If you're from the UK, you're probably familiar with something called the Yorkshire pudding. There's other things that use eggs and flour. But a lot of the recipes we're going to at least try to pull out which ones are noodles and pancakes. And as it turns out from manual review, we've picked out a few of the recipes just to be able to train on. Okay, great. So what we've done here is that for each of the IDs that I could manually pick out as being a noodle or being a pancake, what we're going to go back in is annotate them using this nom over here, these extended vocabulary that we did. We're going to annotate those recipes and say, okay, I know you're a noodle recipe or I know you're a pancake. And so now if we go back in and take a look at our temp.ttl file, the thing that we're building up, we've just serialized out. Temp.ttl, boom. And now you can find, if I look up create, anytime. Yeah, great. Okay, so now, we've got our recipes in there, but if I go back and look at this identifier for anytime crepes, okay, then we should have definitions in there for the bottom. Okay, great. So now we should have definitions added to this annotating whether or not something is a noodle or a batter. And the idea here is what I'm trying to bring out is that we've got a graph, we can apply SPARQL queries to it, but we can do some post-processing on the results that are coming out of the SPARQL queries. And in this case, we came up with some conditional probabilities to try to define a really simple set of rules to distinguish between different things that we could go back in and add annotations to the graph. We can get a lot more complex with this. We can use probabilistic rule sets. But it's stressing the point that you can start to complement with different approaches. You can start to mix and match between a very deterministic kind of query versus some sort of rule system. Okay, now building on that, let's talk about rule systems in a much more defined way using something called SHACL. I'm going to load up EX50. And we're using a library called pySHACL that's built on top of RDFlib, but we do some wrappers over the top of it. And SHACL is a way of defining shapes. If you want to look up, there's a lot of great background on it from W3C. It's a way of defining rules based off of shape constraints. So again, in a knowledge graph, shapes equate to data objects. And by having rules that describe what you expect to see in your shapes, then you can start to pick out different data objects. So here I'm going to define some SHACL. I'm going to say I've got a person shape, and it's going to look at a node, and I'm going to expect to see that for each person, they've got a first name. It's going to be type XSD string and called a given name. And then they've got a birth date, gender, address, etc. The addresses might have postal codes. So once I've defined that, then I've created some rules. And here I've got a real simple graph, and it's just got, okay, here's some people. Here's where they live, or actually a person. somebody named Robert Jr., who helped to define some W3C standards, I believe. What I'm going to do is I'm going to take this RDF, and I'm going to apply the SHACL rules to it. And this is, again, doing it in raw. Boom. And SHACL will print out, okay, here are all the parts that have violated some rule, some constraint, shape constraint rule. In particular, Bob's address didn't really fit the postal code designation. Also, Bob's birth date didn't quite fit. Okay, great. And so SHACL is a way of creating a report, but optionally, what it reports could be coming back as a graph. Now, if I want, I can treat this as a graph, and I can iterate through and take a look at what are the different components that are being reported. Now, that's using SHACL in the raw. If I do this with kglab, trying to make it a little bit simpler, we'll create a graph out of our recipes, like I mentioned before. And now we're going to do a real simple shape. And in this case here, we're going to say it's got to have at least 3 ingredients. And the maximum length of the definition, its label, will be 50. So I'm going to do a little bit of a data quality check on the recipes and just see, let's kick out any of the recipes that don't fit those rules. Great. And so we can get back our report text. And we can take a look and see, okay, interesting. So profiteroles has too long of a label. And looks like there's some tabs in that label too. And also German dumplings, spaCy, one of my favorites. We used to make those at home. And yeah, it's got too long of a name, on and on and on. So the idea that I'm bringing out here is that there can be data quality checks expressed as shape constraints, as SHACL rules. You can apply them to your knowledge graph in general and kick out the ones that are exceptions and then review those. So let's do that. What we're going to do here is to take a look at this report that came back as a graph. It's an RDF graph when we run SHACL. Instead of getting a text report, we can get it back as additional RDF graph. Sort of taking a subset of our knowledge graph and just having the reported parts that we need to troubleshoot. So we're going to take that graph and we're going to query it with this Sparkle query to get a little bit more insight on what it is that's causing the problems. And we're going to report that as a data frame. So now we can use it in pandas, in scikit-learn, etc. And so here we've got just a small set of these recipes that didn't follow the rules that we'd had. You can go into a lot more details with SHACL. The nice thing about it is it's being used for auditing work. It's also being used for data quality checks. It can be used for human in the loop to sort of kick out things that an expert should review. It can be used for inference in certain ways. The nice thing about it is that the rules in SHACL are something that are, relatively easier for people to read and understand. Let me dig back up a rule. This formatting of rules is something that a domain expert who doesn't speak knowledge graph can at least look at and review and say, yeah, this fits our financial audit. So I just want to introduce SHACL, something very, very useful to use. And let me cut back over real quick and see if there are any questions right there. No questions just yet. Yes, yes, Ashley's class is coming up, so I want to wrap up soon. Okay, if no questions yet, let me keep going. There's much more to show. Good. Jenna, can we plug the knowledge graph into spaCy? Great question. Yes, exactly. In fact, that's why kglab was created, was because of spaCy. And so there's another project that's called PyTextRank, and I've been one of the committers on TextRank implementation since 2009. There's a Python version that's relatively popular. A lot of the developers for PyTextRank are also developers on kglab. What we wanted to do was be able to build up knowledge graphs to represent what is being parsed out of text in spaCy pipelines. And so PyTextRank is a pipeline component for spaCy. And there's something called entity linking, where you can provide a knowledge graph, and then when you're doing NLP work, when you recognize entities in the text, link those into the graph. And so that's what we've been building. That's why we built kglab in the first place, was to be able to have RDF representations of, a thesaurus that you can apply, or like a domain-specific vocabulary that you can apply and go in and parse a bunch of documents and pull out the entities from the knowledge graph, so you have everything linked into your graph. And the reason for that is that with text graph, with text rank and the text graph kind of algorithms, they use graph algorithms to pull out the entities from the text. And so there's a very, very nice fit between the two. We don't have that ready yet to show. We've been working on it. Within the next couple of months, we should have a PR where we'll be pushing that live, the kglab integration of PyText rank, and they'll be showing up on spaCy Universe. Really good question. There's a lot of other ways to use knowledge graph where you can, or you can take and have question answering or some type of explainability. But definitely this overlap between NLP and knowledge graphs is really rich. I recently worked on an industry survey about NLP use cases in enterprise, in industry, and the number 4 use case for NLP in industry now is preparing for knowledge graph work, data preparation for graphs. So definitely a lot of overlap there. Okay, let me move on. There's a couple other things I definitely want to show. So I'll go back to sharing. How do I share this thing? There we go, unpause. Thank you. Okay, now let me go to number 6. This gets interesting. So I'm going to open up EX60. We're going to shift into a different area altogether. This is working with graph algorithms. We're going to be using a library called NetworkX. And so let me talk through here. A lot of work in graph algorithms. It's a very, very deep rabbit hole. Long story short, the area of graph algorithms, typically a lot of this work has used, let's take a graph, convert it to a matrix, and run algorithms on our matrix. And that works pretty well when you're using things like, vector processing, like the GPUs. With kglab, we're managing how you make that transform from graph data to matrix data, or graph data to tensor data. So you've probably seen this used before of something called a subgraph. What I'm going to do here is bring in our recipes TTL. We've got a slightly larger version of the graph that we were working with before, but pretty much the same thing as what we just did by adding the vocabulary extension. And here I've got a SPARQL query. This goes back to an earlier question, but I'm going to take a look at recipes and ingredients and represent those as just a sort of a superstructure, backbone, if you will, of subject and object. And let's skip the different relationships. We're just concerned about this one kind of has ingredient relationship. Right? And now what I can do is create what's called a directed graph. So when in knowledge graph, there's directions on the edges, one entity with a relationship to another entity, so that's directed. And there's a special kind of that called a bipartite graph. What that says is that the recipes, at least in this representation that I'm looking at, recipes aren't going to link to each other. Recipes link to ingredients. Also, ingredients don't link to each other. The ingredients are linked by recipes. So this is a simplified view, but it says that the different entities in my simplified view are 2 distinct sets, bipartite sets. That's really helpful when you're doing building search indexes, for instance. But long story short, I'm building up a graph in NetworkX by using kglab. And now I can start to do some graph work with it, graph algorithm work with it. First thing, real simple, I'll just take a look at what's called density. And this tells you a bit about the distribution of nodes and edges, maximum possible number of edges per node. So it ranges from 0 to 1. So here we've got a fairly sparse graph, 0, 1, 6. Just something interesting, especially when you get into larger graphs, to understand like how much compute will be required. And now let's take a look. I've got a node ingredient for butter And I'm just going to get an identifier for it. I'm going to use a transform to get a number to represent that. I'm going to go in and say, hey, let's take and search all the recipes that have butter. Starting from that butter as a starting point, I'm going to do a breadth first search. Actually, nothing. No edges are returned. And so butter is a terminal node. It doesn't connect to anything else. So what I'm going to do is go back and rework this graph. I'm going to convert it from a directed graph into just very simply an undirected graph. So now I basically have a two-way relationship on every edge. And if I do that, boom, now I can show with that simplification, I've relaxed it. Here's, if you hop through all of the recipes that use butter, let's hop over them and look at the other ingredients, look at its neighbors. And so now I'm going to take and look at, okay, let's cut that into sets. I've got this bipartite relationship of all the recipes and all the ingredients that are somewhere clustered around butter. Now, there's a lot of graph algorithms you can use. One thing that's actually pretty useful is something called a topological analysis. I can do something called a triadic census. It comes up occasionally, but it's a way of understanding shapes that occur frequently within a graph. And this actually gets into some ways of being able to generate sparkle and generate PySHACL rules and things like that. It's a kind of processing you could do. Let me go a little bit further. What we're going to do here is take and use a graph algorithm called centrality, degree centrality. We're going to take a look and see which nodes in this subgraph that we're working with are most connected. As it turns out, flour, egg, salt, those are really highly connected. Flour is the most common ingredient. That's one way to look at it. Let's try to visualize that. So we can use matplotlib on the results. Boom. And this is where having a GPU comes in very handy. Okay, taking a bit to show. Boom. And so you can see this distribution of like all the different recipes in this subset, and then out on the edge in red, you've got the different ingredients. We can go in and use a different algorithm though, called kcore, and we can take a look at the maximal connected subgraphs. So now we can start to pull apart the cores, sort of peel off the onion skin, if you will, from our graph by taking a look at the most popular kinds of ingredients. It's a slightly different view than just using a centrality measure. Again, it's like peeling off an onion skin. But what we're trying to do is tease out the relationships amongst all these different types of ingredients. And another variation, a kind of centrality, it's called eigenvalue centrality, is PageRank. You've probably heard of that. And if you run it, it comes up with slightly different rank values, but the same rank order as using in kcore. But again, we're taking a look at some analysis of these popular kinds of ingredients. How do they relate to each other within the recipes? And we can apply rankings, numerical measures of distance between these different ones, which we can use for other types of purposes later on. So I just want to show that in terms of NetworkX, there's a lot of algorithms, a lot of implementations, but you can take an RDF graph and boom, within a few lines of code back up here, you can come from a Sparkle query and start to do graph algorithm analysis. It used to be you'd have to write a lot of custom code, and that might take a few hours to do. That's one of the things we try to simplify. Another thing I'd like to show that's related is about measurement and inference. So I'm going to load up here X70, and I've got a different graph. It's one that's got some relationships, family members who are a bunch of Vikings, very happy Vikings in a village. I'm going to do a measure. So I'm going to take a look and see how many edges are in this graph and how many nodes. I can come back and measure it. Let's query it. And here I'm going to look at who's an ancestor of whom in the graph. And initially, I don't get a lot of results. And part of that is because this is a two-directional relationship that I'm measuring spouse of, ancestor of, things like that. Those can be reflected back. So what I'm going to do is apply something called inference using OWL, using an OWL closure, and I'm going to fill in the missing parts. So if somebody was a child of another node, then I'm going to fill in an additional relationship and say, well, the other node is an ancestor of that child. And it does. It populates out. If you take a look and see, it'll generate a lot more nodes in the graph. If I come back in and measure, you can see many more edges, many more nodes. And if I query, I can come back and get a lot more answers. So I just want to stress this, that you probably want to leverage inference before you start doing a lot of analysis. I can do similar things with Scosify. I know we're coming up on time, so I don't want to go into too much detail on that. But it's something to keep in mind. There are ways to fill in the blanks in a graph by doing that. I know that we're almost out of time for the 2-hour slot. I'll be around. I can answer questions. There's definitely a lot more areas of kglab. We can get into some of the machine learning parts of it. In EX7.1, we talk about probabilistic graphs. And then in 8.0, we start working with some deep learning to deduplicate the ingredients. Definitely have a lot of others about working with CSV files and whatnot. But I hear the audio, so let me pause and go back to, great, in case some questions. Natalie, can you point me to my people? I've been using knowledge graphs to drive systems thinking and analytics teams. Subject matter, okay. Can you share names of people or groups that have specific interests in data science project management? Oh, no, that's a good one. Good question. Project management's great. And oh gosh, there was a really incredible team that I got a chance to talk with at General Electric about 5 years ago. I got introduced to them through my editors. They actually wanted to talk shop. And unfortunately, I left that position. All of my contacts were in the corporate email on my previous job. But inside of GE, they were looking at project management, particularly how to move people between different product lines. What kind of, if you wanted to beef up one line and move people off of one line to another, what kind of training would be required per individual based off of previous accreditation training they had and certification. And it's important for compliance reasons. So they were using knowledge graph and a lot of very deep work in ontology to represent about people and training and product lines. And then that fit into the project management. It was fascinating work. And I'm trying to find out where those people are, but I'm certainly seeing this as sort of data science for project management. I've also seen people who go out and do data mining on the database of JIRA tickets for a project, a software engineering project, to understand and do a graph representation of the problems that were encountered in project management, and be able to predict about costs of new product features. So we can talk more. I'd love to talk offline about that. Thank you very much. A lot of great comments. Oh, great. Yeah, I'd love to connect. NHH did a digital, right? Yes, I'd like to talk more about that. Okay, great. Thanks for kind words. There's a lot more we could cover, but we did cover a lot in 2 hours. And I don't know if I have to jump off the video. If it's possible to stick around, I'm very happy to stick around and answer questions. I'll leave that. I'm not sure, James, what...
I'm not sure on that. Ilias may know the answer. I think there is a technical seat limitation, but hopefully he'll be able to comment on that. But yeah, just a massive thanks from me, Paco, as well, because that was, an incredible session. I've never seen anything like it, if I'm honest, in our space. And so that, yeah, massive thanks. And I managed to fix my Python issue and catch up, so I participated myself.
Thank you kindly. Well, the one takeaway is just, there's a lot of code out there for working with graphs. The people in graph algorithms don't talk to the people doing semantic technologies. Those people don't talk to the people doing graph neural networks, and none of them talk to the people in statistical relational learning. So what we've tried to do within a few lines of Python, can we bridge between these different communities? Instead of writing 3,000 lines of Java, can we just write a few lines of Python and make it simple? That's what we're trying to do. We'd love to work with you all. If you have use cases or things to suggest or any sort of issues you're running into, please let us know. And thank you all very much for this.